Starting from this video, we give a brief introduction to number theory, which is the study of integers. First, let's give a couple of familiar definitions. For integers a and b, we say that b divides a, written as b vertical line a, if there exists integer k such that a equals k times b. We also say that b is a factor of a, or a is divisible by b. We also define the highest common factor, or the HCF, of a and b as the largest positive integer which divides both a and b. For example, 3 divides 15 because 15 equals 5 times 3, where 5 is the k in the above definition. Also, 7 does not divide 15, because if 7 times k equals 15, then k equals 15 over 7, which is not an integer. Also, the HCF of 8 and 20 is 4, while 9 and 14 have no common factors except 1, so their HCF is 1. Now, consider positive integers a and b, where a is greater than or equal to b. By the division algorithm, we know that there exist positive integers q and r, such that a equals q times b plus r, where r is greater than or equal to 0 and less than b. We give an important observation here, which is that HCF of a and b equals the HCF of b and r. To prove this, we show that a and b have the same common factors as b and r. In other words, c divides a and c divides b if and only if c divides b and c divides r. For the only if direction, we write a equals k1 times c and b equals k2 times c for some k1 and k2 in the integers. Then r equals a minus qb, which equals k1 times c minus q times k2 times c. So we can take out the common factor c and write k1 minus q times k2 times c. So c divides r. Conversely, write b equals L1 times c and r equals L2 times c for some L1 and L2 integers. Then a equals q times b plus r, which equals q times L1 times c plus L2 times c. So again we can take out the common factor c to write q times L1 plus L2 times c. So c divides a, and the proof is complete. Using the claim, we can find the HCF of a and b by applying the division algorithm repeatedly. Let's look at an example. Suppose we want to find the HCF of 5817 and 1428. To do this, we first use the division algorithm on these two numbers to write 5817 equals 4 times 1428 plus 105. Using the claim, this means that the HCF of 5817 and 1428 equals the HCF of 1428 and 105. Now, we continue to use the division algorithm on the numbers 1428 and 105. So now we write 1428 equals 13 times 105 plus 63. Again, this means that the HCF of 1428 and 105 is equal to the HCF of 105 and 63. We continue to write 105 equals 1 times 63 plus 42. And again, this means that the HCF of 105 and 63 equals the HCF of 63 and 42. We continue to write 63 equals 1 times 42 plus 21. And again, this means the HCF of 63 and 42 equals the HCF of 42 and 21. Finally, we can write 42 equals 2 times 21 plus 0. This means that 21 divides 42, and the HCF of 42 and 21 equals 21. Since all the HCFs are equal, we know that the HCF of 5817 and 1428 equals 21. From the example, we see that we can have a systematic method to find the HCF of two positive integers a and b by using the division algorithm. This method is known as the Euclidean algorithm. It allows us to find the HCF of a and b using the following steps. First, we let R0 equals a and R1 equals b. This is just for convenience in notation. We use the division algorithm to write R0 equals Q1 times R1 plus R2, where R2 is greater than or equal to 0 and less than R1. If R2 equals 0, then R1 divides R0, so the HCF of a and b is just b. Otherwise, we move on to step 2, where we need to repeat the division algorithm for I is greater than or equal to 1 to write Ri equals Qi plus 1 times Ri plus 1 plus Ri plus 2 until Ri plus 2 equals 0. We know that this must happen because Ri plus 2 is greater than or equal to 0 and less than Ri plus 1 for all I. In other words, the remainders that we get from the division algorithm must be strictly decreasing. In this case, Ri plus 1 divides Ri, so the HCF of a and b equals Ri plus 1. We can identify the quantities stated in the algorithm in our previous example to understand it better. In this case, R0 is 5817 and R1 is 1428. So we apply the division algorithm on R0 and R1 to get Q1, which is 4, and R2, which is 105. Since R2 is non-zero, we have to apply the division algorithm on R1 and R2 to get Q2 and R3, which are 13 and 63, respectively. Notice that R3 is strictly less than R2. We continue to apply the division algorithm to R2 and R3 to get Q3, which is 1, and R4, which is 42. Repeat the division algorithm again to get Q4, which is 1, and R5, which is 21. Finally, we get Q5, which is 2, and R6, which is 0. Since R6 is 0, the HCF is the previous remainder, in other words, R5, which is 21. There's more that we can say about the Euclidean algorithm. For each of these equalities, we can rearrange to write the remainder as the subject. So the first line becomes 105 equals 5817 minus 4 times 1428. The second line becomes 63 equals 1428 minus 13 times 105. The third line becomes 42 equals 105 minus 63. The fourth line becomes 21 equals 63 minus 42. Since the last line have remainder 0, we just ignore it here. Then, we can work our way backwards to write 21 equals 63 minus 42. And then we can substitute the expression for 42 in the second last line to write this as 63 minus bracket 105 minus 63, which is 2 times 63 minus 105. Again, we can substitute the expression for 63 from the second line to get 2 times bracket 1428 minus 13 times 105 minus 105, which equals 2 times 1428 minus 27 times 105. Lastly, we substitute the expression for 105 to get 2 times 1428 minus 27 times bracket 5817 minus 4 times 1428, which equals negative 27 times 5817 plus 110 times 1428. What we have done here is that we have written 21, which is the HCF of 5817 and 1428, as an integer times 5817 plus another integer times 1428. It is no coincidence that we can write the HCF of two numbers in this form, which leads us to the following theorem. This theorem states that if we have two positive integers a and b, then there always exist integers x and y such that ax plus by equals the HCF of a and b. The proof of this result is exactly the steps that we have done in the previous example, which is to reverse the steps in the Euclidean algorithm. This is called the extended Euclidean algorithm. This result is surprisingly useful, and there are two important corollaries, which we will present straight away. The first one is that if C divides A and C divides B, then C also divides the HCF of A and B. That means that whenever we have a common divisor of A and B, this common divisor must also divide the highest common factor. It is easy to prove this using the extended Euclidean algorithm. First, we write A equals k1 times C and B equals k2 times C for some integers k1 and k2. Then, using the above theorem, there exist integers x and y such that the HCF of A and B equals ax plus by, which equals k1 times C times x plus k2 times C times y. We can take out the common factor C to get k1 times x plus k2 times y times C, which means that C divides the HCF of A and B. The second corollary is the following. Suppose we have an integer n. The equation ax plus by equals n has integer solutions x and y if and only if the HCF of A and B divides n. To prove this, we let D equals the HCF of A and B, to simplify the notation. For the only if direction, since D divides A and D divides B, we can write A equals k1 times D and B equals k2 times D for some integers k1 and k2. Then, n equals ax plus by, which equals k1 times D times x plus k2 times D times y, which equals k1 times x plus k2 times y times D. This means that D divides n. Conversely, suppose that D divides n. We can write n equals k times D for some integer k. By the extended Euclidean algorithm, there exist integers x0 and y0 such that ax0 plus by0 equals D, because D is just the HCF of A and B. So we can write n equals k times D, which equals k times bracket ax0 plus by0, which equals kx0 times A plus ky0 times B. This means that x equals k times x0 and y equals k times y0 is a solution to the given equation.